Good morning, everyone. Thank you for joining us. I'm going to put us on pause while everyone logs in. Good morning. Thank you for joining us today. This is Leah Freeberg from Fluke Reliability, and this is a best practices webinar session. You probably know Fluke is a test tool provider, and you may also know that we produce some of the industry's favorite reliability tools, from infrared cameras to vibration meters. But you may not know that many of the measurements that our tools collect now flow automatically into EAM systems of record. It happens via a framework that we call Fluke Connect. Our goal at Fluke Reliability is to better connect asset management data and teams with asset management systems to drive connected knowledge. And of course, that knowledge depends greatly on best practices in condition-based maintenance. So that's why this series of webinars explores reliability maintenance strategies, and that's why we feature speakers from a variety of expert backgrounds. Before the presentation, we have a few housekeeping items to go over. Today's session is being recorded, so your phone lines are muted to minimize background noise. We will be answering questions both during the presentation and afterwards during Q&A. Take a minute now to find the questions tool in the GoToWebinar dashboard. Please feel welcome to submit questions as we go. I will share as many of your questions as time allows for our presenter to answer. If we have unanswered questions at the end, we'll follow up with written answers. If you'd like to receive the slides from today's presentation, please let us know during the survey that will appear at the end of today's session. So don't hang up until the survey appears and you've answered the questions. We're also happy to send you a certificate of attendance after today's webinar. You'll see a question on the survey about getting a certificate. Answer yes, and we'll send one to you. A recording of this webinar in full will be available on the Excelix.com website within a day or two. And that's it for housekeeping. So now for the main event. Today, we are very pleased to have with us Jonathan Gough, an alignment technology expert from PRUFTECHNIK, and he'll be presenting on the most costly pitfalls in laser shaft alignment and how to avoid them. Jonathan, if you'll forward to the next slide, I want to introduce you a bit. So Jonathan is a Fluke Reliability product manager and the product owner for the PRUFTECHNIK Touch Alignment platform. Based in Ismaning, Germany, he has 25 years of experience with PRUFTECHNIK, including roles as head of product management, international sales manager, and general manager for the Southeast Asia territory. He has 30 years of experience in the condition monitoring sector and holds a Bachelor of Engineering degree in Mechanical Engineering from Bradford University in the United Kingdom. So welcome, Jonathan, and thank you for being with us today.
Yeah, hi, morning to you all. It's great to be back.
I understand, Jonathan, that you'll be showing us more of your famous video demonstrations of alignment today.
Yeah, we've sorted out some new infamous interactive alignment situation videos that hopefully highlight, as you mentioned, the common and costly alignment pitfalls. So
right. Okay, well, I can't wait to get started. I'm very excited to see what you've got this time, so I'll turn it over to you now.
Okay, great. Oh, so morning everybody once more. So if you don't know PRUFTECHNIK, maybe just to give you a short introduction, PRUFTECHNIK was formed in 1972, a family-owned company, and it grew into an organization of 20 worldwide subsidiaries. And last year, in July 2019, PRUFTECHNIK was acquired by the Fluke Corporation, and as hopefully we know, Fluke is a company of the Fortec Group. And PRUFTECHNIK is now part of the Fluke Reliability Solutions business unit. Therefore, we're a leading technology manufacturer in the field of condition-based maintenance, rotating equipment, machinery, and plant reliability. And our main focus at PRUFTECHNIK and the products and the solutions we offer is for laser alignment, applications for vibration condition monitoring, and then we use eddy current for the non-destructive testing area of our focus. So that's what we're doing here at PRUFTECHNIK. But we're not only researching, developing, manufacturing, and selling these solutions. We also offer in the industry and in the field worldwide machinery services. As you can see, we have a wide range of industries and applications. For example, turbine alignment. We do roll alignment services. And the main point I want to mention here is that from all this diagnostic and measurement services we perform out in the field, we get a lot of feedback and information from the applications and the industries about the machines, the applications, and even, let's call it, pain points. And this feedback is invaluable. That helps us further develop our products over the years with innovation to allow us to have the products that obviously suit the customer's needs on their application. So that's why it connects with the product offerings, is the services we do as an organization. We want to talk about alignment, and it connects nicely with vibration. Does alignment, because if you've read a lot of surveys and people who've measured out in the field, they'll tell you that over 50% of machine breakdown and failures can be directly attributed to misalignment on the machinery. And the misalignment obviously can create loads, stress, excessive vibration, obviously, as a consequence of the load. There can be heat and energy related to the vibration. And then, as we can see, as well as the vibration, we can load the bearings. Ultimately, we would wear and damage the bearings if we're having misalignment. The same can happen, obviously, on a pump application where we have seals, and definitely mechanical seals have to be quite well aligned and precisely rotating to perform. Does a mechanical seal, otherwise it can leak and damage. And obviously, ultimately, and the most logical when we talk about alignment and misalignment is the wear and the load, and ultimately the damage on the coupling itself or the shafts that are connected by the couple-driven machine. So this is the area that we're looking at, is alignment and the consequences of poor alignment or misalignment. As mentioned in the last webinar, but just to summarize where obviously PRUFTECHNIK has come from, and where the industry of alignment also has moved from. Initially, historically, we would say historically, but still today, some people are using ruler and feeler gauges on some machines and coupling applications in certain situations. There's the ruler and feeler gauge, which would give something in the order of a tenth of a millimeter or 5 micron resolution. This is resolution, not accuracy, resolution. A dial gauge has a resolution of 1/100th of a millimeter on the dial gauge itself, but there are many mechanical and top issues that you have to take care of with mechanical dial gauges out in the field as a user. And then finally, the laser alignment systems, which generally have a micron resolution, which is obviously 0.05, half a 0.05 thou. So as you can see from the three systems or the three methods, each has a factor of 10 in terms of the resolution that the system delivers. So if you're going to do an alignment with a ruler and feeler gauge, you're going to have to be a wizard to get anywhere near the alignment tolerances and what we would call precision alignment rather than rough alignment out in the field. If you're using dial gauges and you're experienced and trained and you know what you're doing and you have experiences, then there are people in the field who are able to do alignment with a dial gauge, but it takes a lot more knowledge and experience than what we would say these days with a laser product is able to offer and deliver for a user in the field. Not only the precision, but also the accuracy of the measurement they perform out on the machinery itself. So this is the methods, and if you're using using a laser product, what depending on the laser product that you're using, the benefits that are promised by laser alignment devices is, as you can see from this example, that if you after year 1 in year 2, 3, and 4, if you start using a laser alignment product, Then you can see the benefits, for example, on the typical pump overhauls and repairs. In this study that was done, there was a 30% drop in the pump overhauls, and of those percentage, a high percentage of the pump overhaul was because that there had to be replacement of the mechanical seal that had failed and leaked. So that shows you the major savings on the pump, if it's a pump-driven machine. And also, every rotating machinery has bearings, and if you have, the more precise the alignment you have of the machine, the less load you will have on the bearing. And obviously, if you have less load on the bearings, as long as the bearing is correctly lubricated, you'll get a dramatic increase in the bearing life itself of the rotating machinery, based on, as you can see on this, the amount of misalignment directly relates to the bearing life. And finally, also the whole application I mentioned before about heat. Heat obviously is energy, and dissipated heat is energy loss. So the better you have the alignment, the less heat you will have on the rotating machinery, and therefore the less energy you'll consume. This is easy for us to directly relate the alignment to the energy it takes to drive the machinery. So this is the promised benefits of laser alignment. So what we'd like to ask is a question to start off. If Leah, you're going to trigger a poll, I believe.
Absolutely, my pleasure. All right, audience, this is your turn to get involved. I'm going to launch a poll that we'd like you to select one answer from. If you cannot select the radio buttons, then you need to minimize your screen size back down. You may have maximized it to see what Jonathan's presenting. What percentage of your coupling-driven rotating machinery is currently aligned with laser alignment tools? So select one. Is it less than 10% of your machinery that you're using laser alignment on, up to 25%, up to 75%, or more than 75%? If you're not using laser alignment tools, then go ahead and select less than 10%, and that'll all work out. So again, we're trying to get a measure of what your current practices are in the audience so that Jonathan can speak to this appropriately. So I've got about 67% of the audience has voted. I'm going to give you another 10 or 15 seconds or so. I know it's a long question to read, so give it a read and select an option. And I'm hoping for about 75% of you to give us your thoughts here, and then I'm going to share the answers with you. All right, it looks like we're there. So I'm going to close and share the results now. All right, so we've got 37% of folks saying less than 10% are doing laser, 20% are doing a quarter, 25%, 16% are doing 75%, and 27% are doing more than 75%. That's fantastic.
That's great. Yeah, it shows what's that? That's 50% or more is what proportion?
Yeah.
So that's about 50, was it? You mentioned anyway. So that's, yeah, it's about 50-50. Less than
Right.
50 or above 50 or less than 50. So that's great. Yeah.
Okay.
Good.
I'm going to hide these
Okay.
results and turn it back over to you now.
Okay. Am I back on?
It's all you.
Great. Okay. So as we'd like to mention here about the pitfalls, even with the laser alignment systems, things can still go wrong. Is maybe a dramatic statement to make, but what we're saying is not every and not all alignment systems necessarily able to not have the pitfalls that we're going to talk about, the costly and common issues when you're aligning machines. So if you're having a basic alignment system, what you may find is that the process, you can compromise the ability to align the machine in a timely manner, depending what you incur when you go to the machine and start aligning. So this is what we want to focus on with, in fact, four alignment applications with 4 potential pitfalls that we want to we want to show you, and then we want to explain hopefully how you can avoid out there in the field, how you avoid the pitfall that we're going to trying to show you with these interactive videos. So let's just go into the first example. And the first example we're talking about is when we class something as having initial misalignment. So what we're saying is either you have a short distance between the couplings with the initial misalignment, or especially if the distance between the shafts is increased because you have a bigger separation between the couplings, maybe potentially you have a spacer coupling. What you'll find is that with an initial misalignment, because of the line over length situation of the laser, you'll find that as you initially start measuring and rotating the shaft application with misalignment, the line over length of the laser causes the laser to come out of the detector. So unfortunately, in that situation, you're not able to measure the alignment position of the machine initially, because the laser is no longer hitting on the detector surfaces. This is a big problem initially when you're wanting to use a laser system, if you have the line over length due to the angular misalignment initially on the machine. So this is a problem. It's a major pitfall out in the field. Just to show what PRUFTECHNIK do a little bit different. We always have the same distance between the detectors. So even on a short distance, we have the same angular resolution and distances between the two detectors. So if, as can also happen on a misaligned machine, we have an initial misalignment, then we have a special procedure we call freeze frame, and I'll show you this in a minute, to overcome the pitfall of the laser starting to come outside the detector range. So this is the summary of what we're going to go through with this first pitfall example. So we're looking here on a standard motor pump application. This is one that PRUFTECHNIK has in our facility, in fact, here in Ismaning. It's a 30 kilowatt motor. It's a standard machine, standard application. There's nothing weird and wonderful about this machine itself. We've got a coupling alignment situation. We've got anti-friction rolling element bearings on this machine. So the scenario is that you're either installing the motor, it's maybe a new installation of the motor pump, you're either overhauling the motor or the pump, you maybe had to replace the impeller, or the motor was having to be rewound, or as I mentioned earlier on the first part of the video, not in this example on the screen, but if you had a longer separation between the coupling shafts, for example, you have a spacer coupling application, you'll have this line over length, or you've got presets. Maybe you've got some initial preset that you have to build into the alignment, so you're not aligning to 0, 0. Then you won't only have initial misalignment, you'll have misalignment cold, because you have a preset on the machine. So these are the typical examples where you'll have the initial angle and parallel misalignment on the machine when you start trying to measure the machine. So this is what we're doing. We're focusing on the coupling and the motor in this example. So if I just go to just about start the video, what we've got is we've got a view of the motor pump, but we've also embedded into the video to allow you to see when I start the video running. We have a screen of the touch device ready to show you what is the system showing and offering the user as he performs the alignment and the measurement. So you've got this interaction between the two. You can see the application and the laser and sensor, and you'll see the screen changing on the device as the measurements performed. So basically what we want to show in the first example is if the laser is moving off the detector plane, how can you measure the initial position of the machine? This is the question. This is the pitfall. Yeah? And the answer to that question, the basic answer for a basic alignment system is that they use the cap of the laser and the sensor units. And what they do is they call it a rough alignment or a pre-alignment. And what they do is they put the cap on the laser sensor heads, And what they do is they start the laser, in this example, at 9 o'clock, and they rotate the heads through 9 o'clock over 12 o'clock to 3 o'clock. And as you can see, the laser moved its position on the cap. So what the user is supposed to do, and this takes a lot of knowledge and experience and it's trial and error, the user is looking not at one laser and one sensor and one cap. They have to look at two lasers and two sensors with two caps, and they have to try manually to guess and work out with this pre-alignment, or we call it rough alignment, how much movement and correction does the user have to do before he can start using the detector without the cap to measure the alignment position of the machine. So they're roughing, you could call it, they're bucking the machine, you know, they're rough aligning the machine. They measure from 9 o'clock to 3 o'clock just to see how much movement there's been with the laser on the cap. Then they're supposed to do it as well vertically. So you can come back to the vertical, and then hopefully you go from 12 o'clock down to 6 o'clock. The problem is, when I say hopeful, is that a lot of times you can't get the 6 o'clock position because the base plate doesn't allow the bracket with the sensor to always get below the motor pump. And then they're supposed to work out how much is up and down, how much is left and right, how much is parallel, how much is angle. Horizontal is not such the problem because you can slide and move the motor laterally, but vertically it's not so easy to pre-align because you're adding and removing shims at the front foot, at the back foot, just to try to get the laser to stay within the detector surface to be able to start measuring and calculating the initial position of the machine. So this is the pitfall. This is the issue, which is called pre-alignment or rough alignment, and this is what we're just showing is the principle that the laser is on the cap, and the user is just looking for the movement and the change of the laser on the cap surface. This is the issue. So what does PRUFTECHNIK do? Well, PRUFTECHNIK doesn't need you to use the cap, doesn't need you to look at a laser and a pointer. We remove the cap basically, as you can see in the video. And then what we do is we start taking the measurements. And after we take an initial point, we start rotating the shaft. And we can see here on the detector surface on the device, the laser is starting to move to the right. So basically what we can do is we can stop the measurement, we call it freeze frame. We can then reposition the single laser into the single sensor. We've frozen the measurement. We're not impacting the accuracy or the precision of the measurement because we've frozen the measurement at this point. Then after we've repositioned the laser back in with the measurement surface, we can take the second point, and then we can continue with the measurement. And as you'll see in this measurement mode, we can take one point, we adjust the laser before the second point, then we take the third point, we get the minimum values. The values are already on the screen. We've got the amber on the coupling rotational arc, but we can take more points. As it's important, the more points you take over the bigger angle, the better is your statistical data and results. So as you can see here, we're going to take the maximum 5 points in this measurement mode. It's over 180 degrees approximately, and it shows us here, if I just stop the video here, this is the repeatability and therefore the precision on the little mini table you can see on the bottom right area of the screen. This shows us how repeatable and how precise was that measurement, even though we use freeze frame to perform the measurement. So this is important. We're not resulting to looking at lasers and caps and just guessing left, right, up, right, forward, front. We're measuring at the coupling. But as well as measuring at the coupling for the initial alignment position, we're also able to calculate what's happening at the feet. And this is the most important information for the user after he's said he has to realign the machine. How much shimming in which motor position does he have to move which amounts? So this is the initial alignment state. We haven't moved the motor yet. We're only measuring the initial state. And then after you've determined the initial state, very often companies want you to record an as found condition of the machine before you're moving the machine to get it hopefully into better alignment and lowering the vibrations. So very often, if you come back in the office, the condition monitoring engineer will say, well, what was the initial condition of the machine? How was it before you started realigning the machine? And this allows us to measure the initial state, document the initial state, save the initial state, and then obviously share the information, not only to the user who has to perform the realignment, but the engineer who wants to document why the machine potentially was vibrating. So this is what we call freeze frame, and I call it standard. Why do I call it standard? Is because we don't only avoid the pitfall with this procedure I just showed you. If we have the sensor line 5 in this second example here, the part B, we can have more interaction and we can have more guidance for the user as he's performing the measurement task. So if I just run the video, you'll see in this example that initially the laser is not positioned into the center of the detector surface, so that the system shows him, whoop, better adjust the laser wheel before you, in which direction, how much. So that's a little bit of user guidance, so that you start in the middle of the range before you proceed with the measurement itself. And then in this, we call it sweep measurement, after the user has started rotating and is measuring, he will get the information when the laser is starting to move close to the edge of the single detector range. So it's it gets a pop-up on the screen. It informs the user you're getting close. You can still measure, you can still carry on, but if you want to, and this is what was accepted, he can adjust the laser back down, as you see in the detector surface. He can reposition wherever he wants on the detector surface. Then he comes out of freeze frame and he carries on the measurement. This is the important point. He carries on the measurement until he gets, again, another good rotational angle, another good set of data, just to freeze frame once more. You can see here where the 3 measurements that were just performed on this example were all within 100th of a millimeter, using the extend freeze frame technology that avoids the pitfall of having to resort to a laser with a cap. So just let's run to the end of the video. That should be the end. Oh, we just normally show the result because we want to prove that it's not just the coupling information we display for the user. You can see in this example that horizontally there's not a lot of misalignment, but vertically, as you can see initially, at the back end of the motor and half the value at the front end of the motor, there's an angular misalignment that should be initially adjusted and corrected. Good. So that was example 1.
Jonathan, can I break in for a moment?
Yeah, sure, please.
I really appreciate seeing the software view in parallel to the equipment alignment, but there's some questions coming in. On this first pitfall, are we understanding correctly that with a double laser system, if you have initial misalignment over length, then you have to use the laser only as a pointer? You don't get any guidance from it?
Yeah, that's the pitfall. That's unfortunately the reality.
Okay.
You can't use a sensor because the laser goes off the sensor range. You have to visually, as a user yourself, manage and move and adjust without any information at the feet and the coupling values. It's trial and error, and that's why it's a pitfall, because it takes a lot of time, and it's trial and error. It's obviously costly. Yeah.
All right. Well, I want to let you get on with them because I know you've got 3 more and I don't want to run out of time. So let's have the next one.
Well, yeah, great. So that was B. Now we're on example 2. What is example 2? Well, example 2 is titled coupling play, or alternatively people call it backlash. And what coupling play is when there's torsional flexibility between the shafts, and effectively the coupling is torsionally flexible to ensure that you don't initially, when you turn on the motor, especially on a gearbox application, you don't directly crunch and load the gears in the gear wheel of a gear coupling, for example. But a lot of couplings have either torsional flexibility or they're just flexible couplings, and they are allowing flex between the 2 shafts. And what we want to show you is the impact when you're having coupling play. What's the impact and what's the costly pitfall for the user who has to perform the alignment in this application situation? So we're going to zoom in, and we're talking about the coupling in this example, just to show what is the phenomena we're going to because it helps to show, we are initially going to have the laser on the cap just to be able to show you, hopefully if you've got a wide enough broadband and you're able to see the video. We're going to start the video, and what Hans is going to do is just going to show by rotating the coupling with the cap on, just for the principle. You can see, if you've got good streaming, that the laser, especially when you start to rotate, the laser is sometimes moving in the, we call it in the x-axis, in the horizontal if it's vertical. So he's getting relative movement between the two shafts because of the flow, the play on the coupling application. So this is just to show you how it looks if you visually want to see this relative movement. But as well as seeing it with the laser pointer, it's easier to show it technically with the detector. So here you can see it's the same movement that Hans is performing. He's getting very quick changes in the X, which unfortunately changes the Y value. And this is the pitfall. If you get a change in the relative position of the two shafts in the two heads, you get a change in the Y value. And this is the no-no. This is what creates the pitfall. And what we're going to show you is if Hans doesn't concentrate, and if Hans doesn't measure, it's a measurement what we call multi-point. If Hans is not concentrating on the two angles that you see on the two heads there, you'll see that the laser is moving sometimes from left to right. You'll see it in a minute. It went to the right. And that was a change of angle. That was the coupling backlash. And what happens is, as you measure and you keep rotating, Hans is not looking at the relative angles of the two heads. He's not concentrating on the relative two angles of the two heads, which is critical. Sometimes he's getting changes between the two heads, and those changes of the two heads impact the values and the calculated results that are ultimately defined. So that's the issue. That's the pitfall, that if you have relative movement between the two heads, you'll have a lowering in precision in the calculated results. So how to avoid the pitfall? This is what PRUFTECHNIK is offering. We have a measurement mode. It's called sweep again. It's with the sensor line 7 heads. And basically what happens in this example, you'll see as it starts, I may have to freeze the video just to show you as it's going. So basically what happens is he starts the measurement, and when he gets over 12 o'clock, what you'll see is the system has detected coupling play. The system, in fact, has therefore removed this data from the data set that's used for the calculation of the measurement result. So what you can see is, and he carries on a bit further, there's a sector in the rotational arc, the coupling rotational arc at the top, as you can see, it's missing. It's missing because it's been removed based on the algorithm that we're tracking and filtering in real time as we're doing the measurement. And therefore, when the measurement stopped, you'll see that the system will inform the user, here we go, that there's been coupling play detected. But this is very important, that the measurement information has already been removed out from the qualified data that's remaining. So even though it's saying it's unreliable, it would be unreliable if the system didn't remove the erroneous data from the accepted data. But the data that's qualified is accepted, and therefore the measurement can continue. And what we're going to show now is an extreme example where what Hans is going to do is he's not going to just have the phenomena of the coupling backlash. He's going to now try to create the maximum risk for the user when he's stopping and starting. He's going quicker. You saw the machine is actually moving slightly. That Hans is trying to stress the coupling, is trying to overload the alignment measurement by giving a lot of erroneous data. You saw on the left side, rough rotation, coupling play, vibration. Oh, here it is. This was the result. So those are all the phenomena that the system tracked, the system monitored, and it removed from the qualified data. And this is what you can see here if we just run to the video, as we can see now. So as you can see, the first measurement is the one we did without tracking the relative positions of the heads. And the second and the third in the list of this table here, you can see on the side, we're within 1/100 of a millimeter. So we're in 1/100 of a millimeter when we turn on the algorithm, we remove the coupling plane, the backlash, and any other phenomena that the system detected. But the first one, as you can see, it had a difference of 400th of a millimeter, because Hans didn't take care of the relative positions of the two heads as he performed a basic measurement. Yeah, so that was the video.
Thank you. May I ask another question here?
Yeah, fire away.
Okay. Is it true what we've just seen that with the analytics, you don't have to have the two heads in the same position to get a precise measurement?
Yeah, that's the benefit, yeah, the analytics avoid the pitfall because the user doesn't have to understand and doesn't have to concentrate and doesn't have to track the two heads as they're rotating and
Nice.
rotating versus each other. Yeah,
Okay, so that's the solution. All right, great, carry on.
So let's go to the third, and the third is a very interesting situation where people ask us sometimes, can we start the alignment when the machine is should we start the alignment when the machine is coupled or uncoupled? This is the question that we get asked out in the field. So if you have an initial misaligned machine and you try to bolt the coupling together, then you'll have some residual forces and you'll have some friction, and in fact the coupling is quite difficult to rotate because you can feel the restriction, and this restriction and these forces that's between the two shafts that the coupling is fighting means that if you measure with a coupling mounted shaft application, what will then happen is you're measuring a bent shaft effectively, and if you measure not the true unloaded position of the machine, then after you measure and you move to those values, you won't correct the alignment in one measure and one move. This is the consequence. So it's very important that if you're installing a machine, or if you're having a coupling that you can feel has restriction and some forces, then we would normally advocate the best situation. Even with tire couplings, even with a flexible coupling called a tire coupling, if you've got parallel or angular misalignment, definitely the parallel misalignment, we call it offset, we'd advise you very often to remove the tire coupling, align the coupling uncoupled, and then reconnect the tire coupling, and then you reduce the risk that any residual forces are not putting the shafts in their neutral state. So this is the topic. This is the application that we're discussing around the coupling. So in this situation, we've pulled back the motor so the coupling is free. And basically what I want to show in the beginning is this is the worst scenario. This is the worst pitfall for the double head systems, because basically just to simulate in this example initially to show you that basically Hans can put the laser and the sensor units in any position in that arc. As long as the laser's firing into the sensor somewhere, just like the previous backlash situation, it's up to the user to manually determine and the user to define where the heads are and where's the two relative angles of the two heads. So it's the maximum risk that the angles of the heads aren't in the same position, that the Y value is changing because of the arc and there's an angle between the two heads. This is all up to the user manually, and it's a huge pitfall that potentially, uncoupled especially, that the user falls into. So just to show you what's the how we avoid the pitfall, what we have is a specific measurement mode that we use, and it's called IntelliPoint. And we use this measurement mode very often if we've got sleeve bearing white metal, or you may call them bibby bearing applications, where you want to move the shaft, and it may not be very easy to move one of the two shafts. That's another reason if you've got friction on one of the machines, you move one side of the machine, and then carefully and slowly you move, in this case, the single laser into the single sensor, and you see with the needle, just see the needle has to come within 1 degree. The measurement can't be performed unless the needle is within the 1 degree between the two heads. And then it automatically checks the stability. It takes the measurement based on only if the values are stable before it starts accepting the measurement. So as you can see, Hans here, he's just rotating one. he then only has to look at the dial. As long as the dial comes within the acceptable range, then it checks the stability, and then it takes the point. So the user doesn't have to look at the inclinometers. The user doesn't have to manually decide when he takes his point. The system controls when the system allows you to take the point, which is only within a degree. And you just slowly and carefully, without worrying about the relative angles between the two heads, you just move one and then you move the other, especially as I mentioned on sleeve bearing applications where you've got a lubrication film. You want to be careful that the measurement's only taken when the application is not rotating in this example. So we're only measuring when everything is stable and is qualified. So as you can see, we're taking nice pi readings. The rotational arc is going up. We've got 5 points. If we carry on, we've got the amber. If we take another point, what's the quality of the measurement? That Hans is nicely performing slowly and carefully. Let's just see this 6 point. It's interesting. So we've got 6 points. Hans is a good alignment engineer. He normally would like to take 7 points over 180 degrees. That's a nice rule of thumb to get a nice arc of the measurement data. The more points, the bigger the angle, the better. So he takes the 6 point. He's within the rotational arc. He's gone green, and he's got the measurement. So that's what we would use to qualify for the two heads that they're in the same relative angles to take the point. But PRUFTECHNIK, what we created is another measurement mode for anti-friction rolling element bearings, ball or roller bearings. We have another very important measurement mode we use. It's called pass mode, and this ensures that uncoupled with the two shafts completely free and in their neutral natural state, we get and we can measure without stopping and starting the positions of the two shafts. So we just rotate the laser through the sensor or the sensor through the laser, and as we do it, we're taking measurements automatically. You see the numbers are going up. 20 points have been taken, now another 24. We'll just speed up this video a little bit. Let's get towards the end. So he's getting to the 180 degree. He'll stop the measurement. And then we can see here, just to show you, between those two measurements, the IntelliPoint and the pass mode, we're within 1/100th of a millimeter, those two different measurements. And the reason is that they're in the neutral state, the shafts. We haven't had the pitfall of worrying about the relative angles of the two heads. That was the third video, Leah.
So Jonathan, I apologize if this is kind of going back to the start, but why did you disconnect the coupling?
Yeah, because we want to remove all the residual forces between them to the two shafts to ensure that we're measuring its neutral state and not a loaded, I call it a banana shaft. Because if you do that, you measure, you get values, you move to the values, but you don't get within tolerance because you're only slowly removing the misalignment rather than splitting the coupling, getting the true state, and then doing one measure and one move. This is
okay.
This avoids the pitfall for the guys.
Okay.
So that's 3. I answer the question, Leah?
Yes.
Okay, so we go to the last one, and this is also very interesting because it also relates to this line over length discussion that I mentioned with the initial misalignment, where you can't use the laser into the detector surface. So this is a similar example, but it's different in that we're talking about moving the machine, not measuring the machine, but moving the machine. So just to run this animated video, if we move a machine with a laser on, very quickly with line over length, we can come off the detector range. And if you want to move the other head, the left head, you still have the line over length. So it's the same with the PRUFTECHNIK system. If you move the machine with the laser on, you'll get the line over length. But, and this is the big but to avoid the pitfall, if you move the machine with the sensor and you don't move the laser, you will not have the line over length problem situation when you're adjusting the machine in live move. And this is a big pitfall, that people start adjusting the machine based on the measurement and the misalignment that they've calculated, and they're not able to move the machine. And it will just show you on the video example. Again, we want to show you with the laser the situation. So just to show you, if the machine is with the laser on the movable and Hans is hiding behind the right side of the motor here, he's going to move the laser the motor laterally from left to right, and you can see there's quite a lot of travel of the laser across the cap of the sensor, just to show you visually how much movement there is because of the line over length. Yeah, so every time he moves the motor with the laser, he's changing quite dramatically the position of the sensor, because the laser over the length is increasing with distance. Unfortunately, what that has as a consequence, if the laser moves if the laser moves based on the distance, what it means, unfortunately, in the end, is you have less sensor range to track the movement you're interested in. So as you can see, he's going from one side to the other side, and he's getting what we call end laser. He's getting a lot of movement on that detector surface just because of the line over length. So if we take the cap off and show again, you can see the raw detector surfaces. He's going from one side and he's got the full range. He's going outside the range of the sensor, not because of the sensor's the issue, but because it's the line over length of the laser. This is the problem that he's encountering in this example. So if he goes to a live move, what you can see is that when he moves the motor live, he gets off the end of the range, and the measurement can't continue in the live move. He's got to the limits of the range of the detector due to the line over length of the laser. So this is the pitfall. This is the issue. Is if the laser's on the movable machine and you have angle over length, you're going to come off the range during the live move. And if Hans repositions now the laser and the sensor, so that he's now going to put, with a single laser and single sensor that PRUFTECHNIK offer, he's going to put the laser on the stationary machine this time, and he's going to put the sensor on the movable machine. So it's the same setup, it's the same movement that Hans is going to perform by adjusting the laser within, by moving the motor within the range of its bolts. You'll see how much laser movement there is if you move the sensor versus the laser staying on the fixed machine, on the stationary, and therefore isn't influenced with the line over length. So we'll just start the video. So this is the reverse example. Now we're moving the motor with the sensor on, and you'll see there's a lot less movement and travel along the detector surface. Why? Because we don't have the line over length anymore. So we can ensure that we have the maximum detector movement irrespective of where the laser is and how far is the line over length of the laser problem effectively. So as you can see, this is the hands moving the motor. If we take the cap off, you can see also in the XY, he's moving from left to right, and he stays well within the detector range, this example. It's the same movement of the same motor, but he has the full detector range because he's not worried now about the line over length of the laser. This is the situation. So when he goes to live move now, when he moves the motor and twists it from left to right with the full range within the bolts, he's never going to come off the detector area, and he can always measure and move the full adjustment from misaligned to aligned in one go. He's never going to have to stop the measurement, the move, do a new measurement, and do a second move after remeasuring. This is how we avoid the pitfall. Yeah.
That is a tricky one. Can you confirm for me? So which machine do we put the laser on to avoid the pitfall?
So it's always the laser. Single laser always should go on the station machine, and therefore we'll maximize the range of the detector, and we won't minimize due to the laser line over length. This is the PRUFTECHNIK value. Yeah.
Okay.
Good. So just to summarize, to help us, what we've seen in the last 30 minutes or more, we have, if you remember, example one. And what was example one? Example one was initial misalignment. And what we're talking about here is we're saying that due to the initial misalignment, we have the line over length situation. And that, unfortunately, they have to use rough alignment, pre-alignment. They have to use the laser on a cap they're not measuring the initial position, therefore it takes a long time. It's inaccurate, takes time. There's no reported documentation or protocol in the initial state on the machine. This is what we summarized. Coupling backlash, as you saw, it's dependent on the relative positions of the heads, and therefore, if you're not aware of coupling backlash and it's happening, it'll be to the detriment of the precision and the accuracy. And what will be the consequence is you'll have to do remeasurements and removes, and therefore it takes longer because the coupling play gives false measurement data. Uncoupled alignment is an extreme version of coupling play. It has the extreme risk that the heads are in a totally different angular position and giving false measurement data that calculates, and it's the same consequence of remeasure and remove, which takes longer to align the machine. And finally, as we just showed recently, hopefully you remembered, with the move itself, we have to, unfortunately, the double laser systems have two lasers that they can't avoid the pitfall. But with a single laser system, as long as you put the laser, as we mentioned, on the station machine, you'll have the full range of the detector surface on the movable machine. This is the pitfall that the PRUFTECHNIK systems can avoid. So, just to summarize, after the pitfall and how PRUFTECHNIK avoids the pitfalls, based on our active situational intelligence, as we showed you, we have this frame measurement technology to ensure we always get the measurement in the initial state. We have the live quality enhancement, where we filter out erroneous and negative measurement data during the rotation itself. Uncoupled, we can have we have special measurement modes to ensure that you get the heads in the same relative angles. And finally, as we saw in live move, it's due to the single laser sensor that we're able to offer this full range of adjustment in the move without having the potential pitfall. The value and the benefits, obviously, to the user is high precision, high accuracy, due to the combination of the single laser sensor technology and the algorithms that ensure that we're fast, we're getting accurate data, and as we saw a little bit from the guidance and the workflow, we're saying that everyone, irrespective of knowledge and experience, is able to use the alignment systems equally. So that was the main section, Leah.
That was a great summary, thank you. There's a lot that you just captured. And so now, audience, with those pitfalls in mind, we're going to ask you another poll question here. And you don't have to be terribly specific about it, but thinking about those scenarios that Jonathan just described, how often have you experienced any of those common pitfalls? And just select one. Is it very often, somewhat frequently, occasionally, or never? And you can lump them all together, right? You don't have to have had all four. So, you know, even if there's just one that's gotten you, go ahead and give us your experience with this. And again, I'm going to hope for about 3/4 of us to have answered. But in the meantime, I want to encourage folks also to submit your questions, because even if we don't get to all of them during the presentation, Jonathan will follow up with you afterward. So this is the time to get your question in as well, while he's got a few more slides left to go. So answer the poll and then type your questions in using the GoToWebinar questions tool. All right, I'm going to close the poll now and share the results with everyone. So 14% say that they encounter these pitfalls very often. 31% are somewhat frequently, 50% are occasionally, and 5% have never experienced these. Jonathan?
Yeah, it's obviously people on the call who are doing alignment.
Yeah, right?
This is reality, yeah. This is,
okay, I'm going to hide
really,
this so that you can keep carrying on, all right?
Let's just, to bring it to conclusion, just to summarize, we talked a little bit about how to avoid the pitfalls, and why we're doing that is because PRUFTECHNIK has this adaptive alignment capability and technology. As just summarizing here, it's a combination of the hardware and the analytics in the software that allow us to have, especially in measure and move, as we've shown, this technology. it's not only for motor pumps, as we've shown today. Yeah, uncoupled is relative, but we also do it obviously on a full range of machines and applications, not only the standard motor pump. And then what we're saying is also is that due to the due to the situation, we're saying every user in every situation should be able to get the same quality, the same measurements, the same results, irrespective of knowledge and experience. This is what we're offering for everybody with the adaptive alignment from PRUFTECHNIK. So just to conclude, if you want more information, if you're interested, then PRUFTECHNIK on our website, we have a special section of the website. If you want to go, you can download, you can get more information. We have some white papers. We have also frequently asked questions content. We list the solutions we're offering in this area. And that's the way to go if you want more information, as well as contacting us. So lastly and not leastly, last and not least, what I'd like to do is just thank my colleague Hans Lenz. He was on the videos, as you saw. He's over 20 years of, over 25 years experience here in Germany. Hans Lenz, my colleague, and here just to show in these current days, in this current situation, we were keeping our social distance, and we were actually tolerancing our social distance, 1.5 meters. So that was it, Leah.
That was an alignment joke. That's pretty funny, Jonathan. Thank you. All right, so folks, keep typing your questions in, and you'll note that Jonathan's email is here on screen. You are very welcome to ping Jonathan directly via email with questions that you want to ask now and afterwards. And again, if we don't get to your question now, we will follow up with you afterward. All right, so Jonathan, are you ready?
I'm ready.
Okay. First question, greetings from Senegal in West Africa. In the case that we have different coupling sizes, which one should we use in the machine when doing the setup?
Oh, for the diameter? What the question is? Well, we should use the diameter where the coupling where the coupling element is. This is what we want to know, is what angular change is the coupling where the coupling element. So it's the maximum diameter where the coupling the rubber or the shims or whatever is the coupling type. That's the actual diameter we want. We don't want the maximum hub diameter. We want technically we want the length of the coupling, the diameter where the coupling is changing its angular movement. That's the major diameter of the coupling that we want to use for the calculation of angularity, or we call it gap. Yeah.
This is probably a quick question, but if you're doing this outside, is there anything you need to do to compensate for sunlight?
No, these days this is very important. You're absolutely right. Now with the common products from PRUFTECHNIK, we have a digital filtration, so we can now measure directly in direct sunlight. We don't have to shade and shield the laser, because we digitally are able to filter the sunlight, and therefore we always receive the energy of the laser into the detector.
Good. What happens if you encounter unbalancing during the alignment?
Oh, that's a good question. Yeah, chicken and egg. I mean, you can't rebalance a fan if you don't remove the alignment before you balance a fan. So in fact, you normally would check for, if you have a fan application and you don't, 1 times RPM, 2 times RPM, you would normally start with alignment. You'd remove the alignment of the coupling of the motor fan, and then you would balance the fan. So you won't have with the forces of the fan. We're not spinning at rotational speed. We don't have dynamic forces. So as long as it's let's say a static rotation of the measurement, we don't get the imbalance forces bending the shaft to get the alignment position. We then realign the motor to the fan to remove the 1-2 times relating to misalignment, and then the person can rebalance the fan, because then he's confident that the 1 times movement is all in balance and there's no influences of misalignment influences his balance calculations.
Excellent. We have a couple of questions here that I'm going to encourage you to respond in more depth via email, Jonathan, about evaluating the analytics and such, because we're almost out of time here. There's another one about specific scenarios, such as with a steam generator and such. So folks, we will get back to you with more specific answers. And in the meantime, Jonathan, if you could forward to the next slide. Because on August 19th, we're going to be welcoming Mike Smith from the Lifecycle Institute to this webinar show. Mike is a well-respected reliability engineering expert. I think you'll really enjoy his presentation, everyone. He has a great session planned for us on building a game plan to proactively manage your assets. And then if you'll go one more slide for me, Jonathan. So there's a bit of a trick here. After I close the webinar, please stay on for just a moment, because we'd love for you to answer the survey. Not only do we want your feedback about today, but in that survey, we'll get your ideas for what else you'd like us to cover. And if you would like a certificate of attendance, there's a question in the survey. Answer yes to that certificate question and we will send you one, all right? And of course, if you answer the survey, we will send you a copy of today's presentation. The full recorded webinar will also be available on Excelix.com in a day or two. And that is it for today. Thank you so much, Jonathan. It was such a pleasure having you on the show today.
Yep, as previously, I enjoyed the session, and I look forward to receiving the questions offline and responding and answering them directly with the people of our email.
Indeed. All right. Well, thanks everyone for joining us. Have a great day and afternoon, and we'll see you next time. Goodbye for now. Thanks, Jonathan.
Yo, thanks a lot. Ciao.